The prairie wind cut different across northern Minnesota. Anders Olsen learned that his first winter in 1843, when smoke poured back into his cabin every time a west wind hit 30 miles per hour, and his fire died to embers while burning through 4 cords of wood in 2 weeks. He had built his chimney exactly the way every mason on the Minnesota frontier was told to build it. Straight fieldstone stack, standard height, simple top opening, proven and trusted. By spring, that same cabin turned into a smoky trap that choked out fires and wasted fuel with every storm. Across the timber country, settlers were losing the same battle in cabins built by the book and failing by the season. Over the next 2 years, Anders quietly adapted an old technique using a flat stone placed above his chimney opening that stopped the smoke reversal, cut his fuel use by 40%, and kept steady heat through the worst gales. What did he understand about wind pressure at the chimney top that every serious builder today needs to know? The settlement of Pine Ridge stretched along a narrow valley where the prairie met the timberline, 40 miles northwest of what would become Duluth. In the winter of 1842, 23 families had carved homesteads from the dense pine and oak stands, following the territorial government's promise of rich soil and timber rights for those willing to brave the Minnesota frontier. Each cabin followed the same blueprint: hewn log walls chinked with clay and moss, shake roof, and a stone chimney rising from the gable end. The design came straight from the Territorial Building Manual, copied from successful eastern settlements where chimneys had warmed families for generations. The manual specified a fieldstone or brick stack rising 12 to 15 feet above the roofline, with a flue opening sized at 1/10 the area of the fireplace opening. Local masons built them exactly to specification. Stack the stones with clay mortar, leave a simple rectangular opening at the top, perhaps add a thin iron damper if materials allowed. The method had worked reliably in Pennsylvania and Ohio, where most of the settlers had learned their building trades. Every cabin in Pine Ridge followed this proven approach, and most families felt confident their chimneys would perform as expected. Anders Olsen had arrived in Minnesota that spring with tools wrapped in oiled canvas and a leather satchel containing his mason's certificates from Bergen. In Norway, he had spent 12 years cutting and laying stone for farmhouse chimneys that endured mountain winds and months of snow load. His hands knew the weight of granite blocks and the proper mix of lime mortar for joints that would hold through freeze cycles. But the Minnesota frontier operated on speed and economy, not the patient craft traditions of his homeland. When Anders offered to build chimneys with extra stone courses and weatherproofing details, settlers politely declined, pointing to the territorial manual and the successful cabins already standing. The Hendrickson cabin sat 200 yards downhill from where Anders was raising his own walls. Eric Hendrickson, a former mill worker from Wisconsin, had built his chimney in late summer following every specification in the manual. The stack rose 14 feet above his roof peak, constructed of local fieldstone with clay mortar and an iron damper ordered from Minneapolis. The work looked solid and professional, exactly matching the dimensions and materials used in the other cabins throughout the settlement. Hendrickson had even paid extra for fired brick to line the firebox, demonstrating his commitment to quality construction. When the first serious storm struck in November, Hendrickson's chimney revealed a problem that the manual had never addressed. Each time the west wind gusted above 25 miles per hour, smoke began pouring back through the firebox opening, filling the cabin with choking gray clouds. The wind would hit the top of the chimney stack and drive air down the flue, completely reversing the draft that should have carried smoke upward. Hendrickson would rush to open windows and doors, but the cold air made the reversal worse, and the fire would sputter and nearly die. Anders watched from his own construction site as Hendrickson fought the same battle night after night. The neighbor would stoke his fire higher, trying to force the smoke up through the reverse draft, but this only fed more fuel to a system that was fundamentally compromised. On calm nights, the chimney worked perfectly, drawing smoke cleanly and maintaining steady heat. But every storm brought the same cycle: wind pressure, smoke reversal, desperate fire tending, and cold rooms despite burning enormous quantities of wood. The temperature inside Hendrickson's cabin told the real story of the chimney's failure. Anders began keeping informal records, noting that when the outside air dropped to 10 degrees Fahrenheit, Hendrickson's interior should have reached 40 degrees or higher with a proper fire. Instead, during wind events, the cabin's temperature would fall to 25 degrees, barely 15 degrees warmer than the bitter air outside. The smoke reversal meant that heat was escaping through windows opened for ventilation, while cold air poured down the chimney to replace the warm air that should have been rising. The fuel consumption revealed the economic cost of the faulty system. In a normal winter, Hendrickson should have burned through 5 or 6 cords of split oak and pine to heat his cabin. But the inefficient draft and constant fire adjustments meant he was cutting and hauling nearly 8 cords, a crushing burden for a man also trying to clear land and prepare for spring planting. The extra work left him exhausted while his family endured cold nights despite his heroic efforts to keep the fire burning. Other settlers began experiencing similar problems as the winter deepened and wind patterns became more severe. The McCready cabin, the Johnson place, and the Larson homestead all suffered from smoke reversal during storms, though none as severely as Hendrickson's. The pattern was consistent. Chimneys built exactly to manual specifications failed when exposed to the prairie winds that funneled through the valley. Families learned to dread the approach of storm systems, knowing they faced nights of smoke, cold, and wasted fuel. Anders observed these failures with the critical eye of a craftsman who had built chimneys to withstand North Sea gales. The territorial manual addressed chimney height and flue dimensions, but ignored the fundamental problem of wind pressure at the stack opening. In Norway, every chimney included some form of cap or shield to deflect wind and prevent downdraft, knowledge passed down through generations of builders who understood that an unprotected opening was an invitation for weather to enter. When Anders mentioned wind protection to his neighbors, they responded with polite skepticism. John Baker, the settlement foreman who supervised new construction, dismissed the idea as unnecessary complication. The manual had been tested in dozens of frontier communities, he argued, and adding extra stonework would slow construction and increase costs. Other settlers agreed, noting that their relatives in Wisconsin and Michigan had never needed special chimney caps. The consensus held that Anders was overthinking a simple problem that would resolve itself once the chimneys had time to establish proper draft patterns. But Anders had seen enough failures to know that the standard method would not improve with time. The physics of wind pressure remained constant, and no amount of seasoning would make an unprotected chimney opening immune to downdraft. As winter deepened and the failures multiplied, he began planning modifications to his own chimney design, drawing on techniques his grandfather had used in Norwegian mountain farms, where wind protection was not optional but essential for survival. As spring arrived in 1843, Anders began quarrying flat sandstone slabs from an outcrop 3 miles north of Pine Ridge. The stone split naturally along sedimentary layers, yielding pieces 20 to 28 inches square and roughly 2 inches thick. Each slab weighed approximately 60 pounds, requiring careful transport by ox cart over the rough logging roads. Anders selected 12 pieces, rejecting any with visible cracks or weak spots that might split under freeze cycles. The stone's fine grain and uniform density made it ideal for the cap system he planned to construct above his chimney opening. The technique had emerged from 2 distinct knowledge traditions that Anders had encountered during his first year in Minnesota. In late winter, while helping an Ojibwe craftsman named Little Bear repair a fallen tree near the settlement, Anders had observed a lean-to winter shelter with an ingenious smoke management system. The shelter's fire pit sat beneath a low opening covered by a flat piece of bark supported on 4 wooden posts. The arrangement allowed smoke to escape sideways beneath the covering while preventing rain and wind from entering the fire area directly. When a strong north wind struck during his visit, Anders watched the smoke continue flowing smoothly outward, while the covering deflected the wind pressure above the opening. The second influence came from correspondence with his uncle Niels, still farming in the Hardanger region of Norway. In response to Anders's letters describing the chimney problems in Minnesota, Niels had sent detailed sketches of traditional Norwegian chimney caps used in mountain farms. These consisted of large flat stones supported on small stone pillars, creating a permanent roof over the chimney opening while leaving gaps for smoke to escape around the edges. The design had evolved over centuries to handle the fierce winds that swept down from the Norwegian peaks. and Niels included specific measurements that had proven successful in his family's experience. Anders adapted both concepts into a hybrid system suited to Minnesota materials and weather patterns. He cut 4 stone pillars, each 6 inches high and 4 inches square, from the same sandstone quarry that provided his cap material. The pillars would support the main slab exactly 2 inches above the crown of his chimney, creating a uniform gap around the entire perimeter. This spacing allowed smoke to exit from all 4 sides while providing complete protection from vertical wind pressure and precipitation. The design required precise measurement and careful installation, but used only local materials that any settler could obtain. Construction began in early June, when Anders had completed the main body of his chimney stack. He mortared the 4 support pillars onto the crown of his chimney at exact intervals, ensuring they were perfectly level using a water-filled wooden trough as a primitive leveling device. The positioning was critical. The pillars needed to be far enough from the flue opening to allow free smoke flow, but close enough to provide stable support for the heavy capstone. Anders measured each distance 3 times before applying mortar, knowing that any error would compromise the entire system. The capstone installation required assistance from 2 neighbors, despite their skepticism about the project. The 60-pound slab had to be lifted 12 feet above ground level and positioned precisely on the 4 pillars without disturbing their alignment. Anders used a rope and pulley system anchored to a nearby oak tree, raising the stone slowly while guiding it into position from below. The final adjustment involved sliding the slab until it extended equally beyond each pillar, creating identical 2-inch gaps on all sides. The completed assembly resembled a small stone table perched atop the chimney, unlike anything else in the settlement. The first major test came in October when an early blizzard brought sustained winds from the northwest at estimated speeds of 35 to 40 miles per hour. Snow drove horizontally across the valley, and most chimneys in Pine Ridge began experiencing the familiar pattern of smoke reversal and draft problems. Anders monitored his own system carefully, noting that smoke continued flowing steadily from beneath his stone cap throughout the storm. The wind struck the top surface of the capstone and deflected upward and sideways, never creating the downward pressure that plagued unprotected chimney openings. Temperature measurements revealed the dramatic difference in performance. Using a simple mercury thermometer positioned 3 feet from his fireplace, Anders recorded interior temperatures of 42 degrees Fahrenheit when the outside air measured 8 degrees, maintaining a 34-degree differential even during peak wind conditions. His fuel consumption during the 3-day storm totaled 1 1/4 cords of mixed hardwood, substantially less than the 2 cords he had anticipated based on his neighbor's previous experience with similar weather. The contrast with nearby cabins provided clear evidence of the cap's effectiveness. The Johnson place, located just 400 yards to the east, suffered severe smoke problems throughout the storm. Anders could see smoke pouring from their open doorway during wind gusts, and Johnson later reported burning nearly 2 1/2 cords of wood while still struggling to maintain comfortable temperatures. The Larson cabin experienced similar difficulties, with Mrs. Larson mentioning that they had been forced to sleep in their root cellar on the worst night to escape the smoke that filled their main room. Word of Anders' success during the October storm spread quickly through the settlement, though reactions remained mixed. John Baker acknowledged that the stone cap had clearly prevented smoke reversal, but questioned whether the extra construction time and materials justified the improvement. He calculated that Anders had spent an additional 2 days on cap construction and used stone that could have been applied to other building projects. Several settlers expressed concern about the weight of the capstone, worrying that it might eventually crack the chimney crown or cause structural problems. Other neighbors showed genuine interest in understanding the technique. Eric Hendrickson visited Anders' cabin twice to examine the cap construction and ask detailed questions about the pillar spacing and stone selection. Patrick McLeod, an Irish stonemason who had recently arrived from Pennsylvania, spent an entire afternoon studying the installation and declared it superior to any chimney protection he had seen in his 20 years of masonry work. McLeod particularly appreciated the uniform gap spacing, noting that it would prevent wind from creating pressure differentials that could still cause draft problems. As winter deepened, Anders continued refining his understanding of the cap's performance under different conditions. Light snow accumulated on top of the capstone without affecting smoke flow, while heavy snow loads required occasional clearing to prevent ice buildup around the edges. During periods of calm weather, the system worked identically to a conventional chimney, but its advantages became pronounced whenever wind speeds exceeded 15 miles per hour or when precipitation threatened to enter unprotected openings. The spring rains of 1844 brought a different challenge that Anders had not anticipated when designing his stone cap system. During a 3-day downpour in late April, he noticed that his interior fire struggled to maintain its usual vigorous draft despite the absence of wind. The flames flickered weakly, and smoke lingered near the hearth opening before eventually finding its way up the flue. His thermometer readings showed the fireplace temperature dropping from 115 degrees Fahrenheit to 90 degrees within 2 hours of rain beginning, even though his stone cap successfully prevented any direct water entry from above. The problem lay within the chimney stack itself, where moisture was penetrating the fieldstone and mortar joints. Minnesota's freeze-thaw cycles had opened hairline cracks in the clay mortar between stones, creating pathways for rainwater to seep into the interior surface of the flue. As this moisture evaporated from the heated stone, it cooled the rising exhaust gases and weakened the natural draft that pulled smoke upward. Anders could see water stains on the interior stones when he peered up the flue with a mirror and candle, evidence that his carefully constructed stack was absorbing precipitation like a sponge. The Norwegian solution to this problem involved lining the interior of the flue with a specialized mortar made from clay mixed with fine wood ash. Anders's grandfather had taught him this technique for mountain chimneys that faced months of snow melt and spring rains. The ash-clay mixture created a smoother, less porous surface that shed moisture rather than absorbing it, while the fine particles filled microscopic gaps that allowed water penetration. The lining required specific proportions, 3 parts clay to 1 part ash, mixed with just enough water to create a workable paste that could be troweled onto vertical surfaces. Anders began preparing materials in early May, collecting clay from a riverbank deposit 2 miles upstream from the settlement. The clay needed to be fine-grained and free of organic matter that would decay and leave voids in the finished lining. He processed the material by spreading it in thin layers to dry, then crushing and sifting it through a wooden frame strung with horsehair to remove stones and debris. The wood ash came from his own fireplace, but only hardwood ash was suitable. Pine and other softwood ashes contained too much resin and created a brittle mixture. Application of the clay ash lining required working from the top of the chimney downward, reaching into the flue with long-handled trowels to coat the interior surfaces. Anders removed his stone cap temporarily, allowing access to the flue opening from above. He applied the lining in sections, working approximately 2 feet at a time and allowing each section to set before proceeding lower. The work was physically demanding, requiring him to lean over the chimney opening while manipulating tools in the confined space of the flue. Each section needed to be smoothed to a uniform thickness of approximately 1 inch, thick enough to provide moisture protection, but not so thick as to significantly reduce the flue opening. The second element of moisture control came from observing Ojibwe winter shelters during a visit to Little Bear's extended family camp in late spring. While examining a permanent cooking shelter, Anders noticed a shallow channel carved into the stone base beneath the fire pit. Little Bear explained that this groove carried away water from melting snow or rain that might otherwise pool around the fire area and create dangerous steam or extinguish flames. The principle could be adapted to chimney construction by creating a drainage path at the base of the flue to intercept any moisture that penetrated the stack and direct it safely away from the firebox. Anders implemented this drainage concept by chiseling a shallow channel into the stone hearth at the base of his chimney. The channel measured 3 inches wide and 1 inch deep, running completely across the width of the chimney base and connecting to a small drain pipe that led outside through the cabin wall. Any moisture that entered the chimney and ran down the interior walls would collect in this channel rather than pooling around the firebox or evaporating back into the flue. The drain pipe consisted of a hollowed wooden tube sealed with pine pitch, angled slightly downward to ensure positive drainage away from the foundation. The third component addressed moisture entering through the chimney crown itself. Anders mixed a lime wash using quicklime obtained from Minneapolis, slaked with water, and applied as a protective coating to the exterior stone surfaces above the roofline. The lime wash penetrated slightly into the stone pores and then hardened into a water-repellent surface that would shed rain rather than allowing it to soak into the mortar joints. He applied the coating with a stiff brush, working it into all joints and crevices where water might accumulate. The effectiveness of these moisture control measures became evident during the fall rains of 1844. A September storm brought steady precipitation for 4 days, with temperatures fluctuating between 40 and 50 degrees Fahrenheit. Anders monitored his hearth temperature throughout the event, recording readings that remained steady at 110 degrees despite the continuous rainfall. His fuel consumption during the 4-day period totaled 1 1/2 cords, comparable to his usage during dry weather of similar duration and temperature. The contrast with neighboring cabins demonstrated the importance of moisture management. Eric Hendrickson, still using his unlined chimney despite installing a makeshift metal rain cap, reported significant draft problems during the same storm. His interior hearth temperature dropped to 85 degrees on the second day of rain, and he burned through 2 full cords of wood while struggling to maintain adequate heat. The McCready cabin experienced similar difficulties, with persistent smoke problems that forced the family to keep windows partially open despite the cold rain. Anders documented the performance difference by measuring soot accumulation at the end of the fall season. His lined and drained chimney showed approximately 1/4 inch of soot deposit on the interior surfaces, while Hendrickson's unprotected flue had accumulated nearly 1/2 inch of the same material. The reduced soot buildup indicated more complete combustion and stronger draft in Anders's system, direct evidence that moisture control improved overall chimney performance beyond simple rain exclusion. Patrick McLeod visited Anders's cabin in November to examine the lining technique and drainage system firsthand. McLeod had encountered similar moisture problems in Pennsylvania chimneys, but had never seen the ash clay lining method. He tested the surface hardness with a steel knife, noting that the lining had cured to a ceramic-like consistency that resisted scratching and showed no signs of cracking or spalling. McLeod declared the technique superior to the imported fire brick linings he had used previously, particularly given the local availability of materials and the lower cost of installation. The integrated system of wind protection and moisture control had transformed Anders's chimney into a reliable heating system that performed consistently regardless of weather conditions. The stone cap eliminated downdraft problems, while the interior lining and drainage system prevented rain and snow from compromising draft efficiency. The combination addressed the 2 primary failure modes that plagued standard frontier chimneys: wind reversal during storms and moisture penetration during wet weather. The spring of 1845 revealed a limitation in Anders's chimney system that his previous innovations had not addressed. While his stone cap and moisture controls had eliminated smoke reversal and rain penetration, he observed that his cabin still lost substantial heat overnight when the fire burned down to coals. The problem lay in the rapid escape of hot exhaust gases through the flue, carrying away thermal energy that could have been captured and stored in the surrounding masonry. Anders measured this heat loss by recording interior temperatures at midnight and again at dawn, finding that his cabin dropped from 40 degrees Fahrenheit to 28 degrees during 8-hour periods with only banked coals maintaining the fire. The standard firebox design used throughout Pine Ridge contributed to this inefficiency. Most settlers had built their hearths with minimal stone mass, using just enough field stone to contain the fire and support the chimney stack above. The hearth base typically measured 4 feet wide by 2 feet deep, with side walls only 8 inches thick, extending 3 feet in height. This lightweight construction heated quickly, but stored little thermal energy, allowing most of the fire's heat to escape directly up the chimney rather than radiating into the living space over extended periods. Patrick McLeod had arrived at Pine Ridge in late winter, bringing knowledge from Irish and Scottish stone masonry traditions practiced in the Appalachian Mountains. McLeod had spent 15 years building hearths for mountain cabins in Pennsylvania, where families needed maximum heat retention during long, cold nights. He sought out Anders after observing the unique stone cap system, curious about the Norwegian techniques that had produced such effective results. Their first conversation revealed that MacLeod possessed complementary knowledge about thermal mass that could address the heat retention problems Anders had identified. MacLeod described the heavy hearth systems used in Ulster Scots cabins throughout the Pennsylvania mountains. These constructions employed massive fieldstone bases measuring 6 feet wide by 3 feet deep, with stone slabs 2 inches thick forming the hearth floor. The side walls extended to 6 feet in height and measured 18 inches thick, creating substantial thermal mass that absorbed heat during active burning and released it slowly over many hours. MacLeod had recorded temperature differences in cabins using heavy versus light hearth construction, finding that thermal mass could extend comfortable heating by 4 to 6 hours after the active fire died. Anders began implementing MacLeod's thermal mass principles in May, quarrying additional fieldstone from the same outcrop that had provided his cap materials. The expanded hearth required dismantling his existing firebox and rebuilding with nearly twice the stone volume. He laid a new hearth floor using flat sandstone slabs measuring 2 inches thick, carefully fitted and mortared to create a seamless surface 6 feet wide and 3 feet deep. The increased size allowed for larger fires and provided more surface area for heat absorption and radiation. The sidewall reconstruction proved more challenging, requiring precise stone cutting to achieve the 18-inch thickness MacLeod recommended. Anders selected dense fieldstone pieces, rejecting any with visible cracks or weathering that might compromise their heat. Retention properties. Each course required careful leveling and solid mortar joints to ensure structural integrity under thermal expansion and contraction cycles. The completed walls rose 6 feet from the hearth floor, creating a massive stone structure that dominated the interior of the cabin. MacLeod also introduced the concept of a horizontal flue channel that would slow exhaust gases before they entered the vertical chimney stack. This technique came from Irish cottage construction, where a short horizontal passage at the base of the chimney forced hot gases to travel laterally through additional masonry before rising up the flue. The horizontal section increased the contact time between exhaust gases and stone surfaces, allowing more heat transfer to the thermal mass while maintaining adequate draft for clean burning. Anders incorporated the horizontal channel by modifying the junction between his firebox and chimney stack. He built a stone passage 12 inches long and 8 inches high, connecting the back of the firebox to the base of the vertical flue. The passage was lined with the same clay-ash mixture used in his chimney, providing a smooth surface that would not impede gas flow while maximizing heat transfer to the surrounding stone. The channel angled upward slightly to maintain natural draft, while forcing exhaust gases to give up additional thermal energy to the masonry walls. The final element of the thermal retention system involved installing an iron fire door with an integrated damper mechanism. Anders ordered this component from a foundry in Minneapolis, specifying a door size to fit his expanded firebox opening. The door included a sliding ash pan beneath the main opening, allowing for air control when the fire was banked for overnight burning. Most importantly, the door could be closed completely when the fire died, preventing cold air from being drawn down the chimney and eliminating the heat loss that occurred in open firebox systems. Installation of the fire door required building a precise stone frame that would accommodate the iron components while maintaining an airtight seal. Anders used fire-resistant clay mortar around the door frame, ensuring that expanding iron would not crack the surrounding stonework. The ash pan mechanism required a separate opening below the main door, with its own sealing system to prevent unwanted air infiltration. The completed installation allowed complete control over airflow, enabling Anders to maintain controlled combustion during active burning and prevent heat loss during dormant periods. Field testing during the winter of 1845 demonstrated the effectiveness of the integrated thermal mass system. Anders recorded interior temperatures during a week of particularly cold weather, when outside temperatures remained below 0 degrees Fahrenheit for 5 consecutive nights. With fires banked at midnight, his cabin maintained interior temperatures of 32 degrees at dawn compared to the 28 degrees he had measured with his original lightweight hearth. The 4-degree improvement represented a significant increase in comfort during the coldest hours before sunrise. Fuel consumption measurements revealed even more dramatic improvements in system efficiency. During the test week, Anders burned 3½ cords of mixed hardwood to maintain comfortable temperatures, compared to the 5 cords he had used during similar weather the previous year. The thermal mass stored heat during periods of active burning and released it gradually throughout the night, reducing the need for frequent fire tending and additional fuel loading. The horizontal flue channel contributed to this efficiency by extracting additional heat from exhaust gases before they escaped through the chimney. The contrast with neighboring cabins validated the importance of thermal mass in frontier heating systems. Eric Hendrickson, still using his original lightweight hearth despite adding a rain cap to his chimney, reported burning 6 cords during the same cold week, while achieving interior temperatures that rarely exceeded 25 degrees during early morning hours. The Johnson cabin, built with slightly heavier stone construction, performed better, but still required 4½ cords to maintain similar comfort levels. McLeod examined the completed system in February, measuring stone temperatures at various points throughout the thermal mass. He found that the hearth floor reached 140 degrees Fahrenheit during active burning, while the side walls achieved temperatures of 90 to 100 degrees. These temperatures persisted for 6 to 8 hours after the fire died, providing continuous radiant heating that maintained comfortable conditions without additional fuel consumption. McLeod declared the system superior to any hearth construction he had encountered in Pennsylvania, combining Norwegian wind protection with Irish thermal mass principles to create a uniquely effective heating solution. The winter of 1846 brought the most severe weather conditions Pine Ridge had experienced since the settlement's founding. A high-pressure system settled over northern Minnesota in late January, creating a temperature inversion that trapped Arctic air in the valley for 17 consecutive days. Thermometers registered -20 degrees Fahrenheit on the warmest afternoons, dropping to -35 degrees before dawn. Sustained winds from the northwest averaged 15 miles per hour throughout the period, with gusts reaching 40 miles per hour during the worst storms. The combination of extreme cold and persistent wind created conditions that would test every heating system in the settlement to its absolute limits. Anders had completed his integrated chimney system the previous fall, combining all the innovations developed over 3 years of experimentation. The stone cap provided wind protection, the clay ash lining prevented moisture intrusion, and the massive thermal hearth with horizontal flue channel maximized heat retention. The system had performed well during normal winter weather, but the extended deep freeze would reveal whether the combined techniques could maintain livable conditions during truly extreme circumstances. Anders prepared by splitting an additional 2 cords of seasoned oak and maple, stacking the wood inside his cabin to prevent freeze-related splitting that would reduce burning efficiency. Comparative measurements during the first week of the cold snap revealed dramatic performance differences between Anders's system and conventional chimney construction throughout the settlement. While outside temperatures remained below -20 degrees, Anders maintained interior temperatures averaging -2 degrees Fahrenheit, representing a 33-degree differential above ambient conditions. His fuel consumption during this period totaled 1¾ cords, burned in carefully controlled loads that maximized heat extraction from each piece of wood. The thermal mass absorbed and radiated heat so effectively that he needed to add fresh wood only twice during each 24-hour period, maintaining continuous warmth with minimal fire tending. The contrast with neighboring cabins demonstrated the cumulative failure of standard frontier heating methods under extreme conditions. Eric Hendrickson's cabin, despite his improvised metal rain cap, could achieve interior temperatures no higher than -15 degrees when outside air reached -35. The lightweight hearth construction provided no thermal storage, requiring constant fire maintenance to prevent complete heat loss. Hendrickson burned through 3½ cords during the same week, nearly double Anders's consumption, while achieving interior conditions that remained dangerously cold for extended periods. His family was forced to sleep in layers of blankets directly beside the fireplace, abandoning the rest of the cabin to sub-freezing temperatures. The Johnson and McCready cabins fared even worse, with standard chimney stacks that suffered multiple downdraft events during wind episodes. The combination of cold temperatures and persistent winds created pressure differentials that overwhelmed their unprotected chimney openings, forcing smoke back into living spaces and extinguishing fires at critical moments. Both families reported interior temperatures dropping below -20 degrees during the coldest nights, requiring emergency relocation to neighbors' cabins to prevent frostbite injuries. Their combined fuel consumption exceeded 8 cords for the week, depleting wood supplies that should have lasted through March. Samuel Reed, the county Mason leader who had arrived in Pine Ridge during the previous summer, made detailed observations of chimney performance throughout the extended cold. Reed had supervised heating system repairs across 3 counties, giving him extensive experience with frontier chimney failures and their consequences. He visited Anders's cabin on the 9th day of the freeze, measuring stone temperatures with an iron poker and documenting the system's operational characteristics. Reed found that the hearthstones maintained temperatures above 60 degrees Fahrenheit, even when the fire had been banked for 6 hours, providing continuous radiant heating that eliminated the cold zones typical in cabins with lightweight construction. Reed's examination revealed integration effects that multiplied the benefits of Anders's individual innovations. The stone cap prevented wind pressure from disrupting the natural draft created by the thermal mass, differential between the hot hearth and cold outside air. The moisture-resistant lining maintained optimal flue temperatures, ensuring that exhaust gases rose efficiently through the horizontal channel without cooling and creating backdraft conditions. The thermal mass absorbed peak heat during active burning periods and released it gradually during banked fire intervals, creating steady interior conditions that required minimal fuel input to maintain. The technical validation convinced Reed to advocate for adopting Anders's techniques in new construction throughout his jurisdiction. Reed had authority to specify chimney requirements for county-funded buildings, including schools and municipal structures that needed reliable heating systems. He drafted detailed construction specifications based on Anders's methods, including stone cap dimensions, clay ash lining procedures, and thermal mass requirements. Reed's specifications became the first official documentation of the integrated system, establishing standards that other masons could follow without requiring direct instruction from Anders. Patrick McLeod began implementing modified versions of the system in 3 cabins under construction during the spring of 1846. McLeod adapted the techniques to available materials and client budgets, creating simplified versions that retained the essential principles while reducing construction complexity. His first installation used a timber cap supported on stone pillars instead of the solid stone slab, achieving similar wind protection at lower material cost. The second cabin incorporated thermal mass principles using locally fired brick rather than fieldstone, while the third used a metal liner instead of clay ash coating for moisture control. The performance data from McLeod's installations provided evidence that the underlying principles could be successfully adapted across different materials and construction methods. All 3 cabins achieved fuel savings of 30 to 40% compared to standard construction, while maintaining superior interior comfort during cold weather. The timber cap installation proved particularly significant, demonstrating that effective wind protection could be achieved without the quarrying and transport challenges associated with large stone slabs. McLeod's documentation included detailed drawings and material specifications that enabled other craftsmen to replicate the techniques without direct supervision. Word of the system's performance during the 1846 freeze spread beyond Pine Ridge through Reed's county network and McLeod's professional connections. Mason crews in adjacent counties began requesting information about the stone cap and thermal mass techniques, leading to installations in settlements as far as 60 miles from the original site. The territorial building inspector included references to wind protection and thermal mass in updated construction guidelines distributed throughout Minnesota, marking the first official recognition of principles that had emerged from Anders's frontier experimentation. The economic impact of fuel savings became increasingly significant as settlement populations grew and wood supplies near established communities became scarce. Families using Anders's integrated system reported heating cost reductions of 35 to 50% compared to conventional construction, savings that accumulated to substantial amounts over multiple winter seasons. The reduced wood consumption also decreased labor requirements for cutting, splitting, and hauling fuel, freeing settlers' time for other productive activities essential to frontier survival. Long-term durability observations validated the construction methods used in Anders's system. 5 years after installation, the stone cap showed no signs of cracking or displacement despite exposure to repeated freeze-thaw cycles and wind loading. The clay ash lining remained intact and effective, with minimal maintenance requirements beyond annual cleaning of accumulated ash deposits. The thermal mass construction proved equally durable, with mortar joints showing no significant deterioration and stone surfaces maintaining their heat absorption and radiation properties. The principles embodied in Anders's chimney system began appearing in regional building traditions throughout the upper Midwest, adapted to local materials and climate conditions, but retaining the essential elements of wind protection, moisture control, and thermal mass integration. By 1850, stone caps had become standard features on chimneys throughout windy prairie districts, while thermal mass hearth construction was widely adopted in areas where extended heating seasons made fuel efficiency critical for economic survival. Modern engineering analysis confirms that Anders's innovations addressed fundamental physical principles that remain relevant to contemporary chimney design, validating traditional knowledge that emerged from careful observation and systematic experimentation under frontier conditions.